What did you come up with for the signs of this angular velocity and angular acceleration? Well, the angular velocity is the easy part. Our convention is that counterclockwise is positive, and this is going clockwise, and so the angular velocity must be negative. The angular acceleration is a little harder to figure out. But look at it this way. We know that the angular velocity is negative, and the disk is slowing down, so the angular velocity of this piece of gum must be getting smaller, in other words, less negative. And so the angular velocity versus time graph could look something like this. And that shows us that the slope of the angular velocity versus time graph is positive, or in other words, the angular acceleration is positive. Another way of looking at it is by thinking of the fact that the angular velocity is in the clockwise sense, right? Sense is like direction, but there are only two senses, clockwise and counterclockwise. So it's not like direction of a vector, right? This is really of an angular velocity component. It doesn't have direction, but you can think of it as having sense. And we know that when an acceleration is opposite in direction to a velocity, then an object slows down, and very similarly, if an angular acceleration is opposite in sense, or opposite in sign, to an angular velocity, then the object slows down. So the angular acceleration must be of opposite sign to the angular velocity, since this object is slowing down. Let's move away from angular velocity and angular acceleration and back to what's more familiar from earlier in the course, velocity and acceleration. Because after all, acceleration is the thing that is directly related to the vector sum of forces on an object, not the angular acceleration, but the ordinary acceleration. And the velocity is the thing that's directly related to the momentum of the object, or the speed, which is the magnitude of the velocity, is directly related to the kinetic energy. So while the angular variables are very convenient for describing the motion, they're not as closely related to momentum and energy and what forces do. So we need to be able to move back and forth, and we'll see how to do that in the next video lecture. But let me just remind you that in two-dimensional motion we saw that we can always decompose the acceleration into a parallel component and a perpendicular component. And the parallel component is responsible for changing speed, and the perpendicular component is responsible for changing direction of velocity. Well, exactly the same thing happens in circular motion. So here's a circular motion, and you can see this is an object that's speeding up. I've showed the vector subtraction that gives us this acceleration vector. Well, as always, we can decompose that acceleration into a perpendicular component and a parallel component. But in circular motion, it's convenient to give these different names because of the way we talk about circles. So, although these are exactly the same thing, we'll tend to talk about them using different words and different symbols. The perpendicular component is what we will call the radial component, because it points along the radius of the circle. And the parallel component of the acceleration is what we will call the tangential component, because it points tangent to the circle. So I want to stress, these are nothing new. They are just the parallel and perpendicular components of the acceleration that we've already seen earlier in the course. We're just giving them names that are convenient for when we talk about circular motion. And they play exactly the same roles we've seen. The radial component is the one that curves the path, changes the direction of the velocity, or you could say it keeps the object on the circle. And the tangential component is the one that's responsible for the object speeding up or slowing down. One more thing to notice about the tangential component, since it's the part that's responsible or describes speeding up or slowing down of the object, if the object speeds up or slows down, then the angular velocity must be changing. And so that tells us that the tangential component of the acceleration must be closely related to the angular acceleration, which describes the rate of change of angular velocity. We'll see that relationship between the tangential and angular accelerations in the next video lecture.